Is it on? Okay. So, the first slideshow, and if you want to follow along on PCs or what have you, was basically, you start off with the periodic table. Okay? Your little periodic table. Now, who has their periodic table here?
Me.
The one, you should have that with you at all times. Pull out your periodic tables, because we had some key points. No, not that one, Blair. The one that you made notes on. The one that has the entire Year 9 curriculum on the back. Pretty much every day. British, I'm going to steal yours. No, thanks very much. That's not done at all. That is the periodic table that you should have. That is the Year 9 notes on the back. I mentioned this before. I said that is effectively a cram card that you should have. So, what should your periodic table show? You should have, for a start, what are groups? Do they go across or do they go down? Down. Groups go down the periodic table, and as you go down the table, are you more reactive or less reactive? More. So it's more reactive as you go down. And as you go across, it is also more reactive. Okay? Now, of the 8 groups that there are, I'm just going to put that there, 1, 2, 3, 4, 5, 6, 7, and 8. Of those 8 groups, the number 8 are the noble gases, which don't react. Fine. Now, what is the definition of an ionic bond? Straight from Year 9. Ionic bond. When you get, sorry, a metal and a, yes, one. It's on the back. Okay, long story short, group 1, 2 and 3 are metal electron donors, where group 1 will donate 1 electron, group 2 will donate 2 electrons, and group 3 will donate 3 electrons. That's on the back as well, up the top here. Groups 5, 6 and 7 are non-metal electron acceptors. And group 5 will accept how many electrons? 3, because 3 additional electrons will get its valence shell up to 8. Remember that we want a valence shell configuration identical to a noble gas. What are the 2 things that atoms want? The crying baby scenario that I told you. To be electrically neutral and to have a valence shell identical to that of a noble gas would be a better definition. Full is like a Year 8 definition, but the shells, the first shell on the periodic table is the K shell. It can hold 2 electrons. The second period going across is the L shell. It can hold how many? 8. And the third period that you deal with can actually hold 18, but 8 is that magic number. And the noble gases always have 8 in the valence shell, except for helium, which has 2. But it has 2, it does have a full valence shell, and neon does have a full valence shell, but everything else thereafter doesn't. They just have 8. Yes?
What's the point of it being able to hold 18 if it only actually holds 18?
It holds 18 later. Okay, and that's where the transition elements come in. So I did work through that in class. It will, when you go further down the periodic table, it does start to fill up. Yeah, and so it's not quite as straightforward in terms of filling as you might like, where it's just sort of tick, 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 tick. There's a bit of fiddling going on. But these are metal donors, these are metal acceptors, and an ionic bond is when a metal donor and a non-metal acceptor, it's a bond between a metal and a non-metal, it's an electrostatic bond, which which means they stick together, because the metal electron donors, do they become positive after they donate or negative?
Positive.
Yeah, they become positively charged, and the non-metal electron acceptors become negatively charged, and they will stick together, and that's an electrostatic bond. So an ionic bond is functionally when a metal and a non-metal, a metal electron donor and a non-metal electron acceptor stick together because of, electrostatically, because of opposing charges. Okay, and the product they form is a salt. Okay, that's in what configuration? It's a latticey structure. Yeah, a crystal lattice. Okay. Now, how does an ionic bond compare to a covalent bond? What's the difference between an ionic and a covalent bond? Yeah, that's the key point. The covalent is non-metal, always. They form discrete molecules. They form discrete molecules like H2O. And what are the non-metal and the non-metal doing by way of electrons to get an electron shell configuration the same as a noble gas, and at the same time having electrical neutrality? Yeah, they're sharing electrons. So a simple example. Now, so in the periodic table, which groups are the non-metals? Which groups have elements in the jigger? That component up there.
4, 5, 6, 7.
Yeah, 4, 5, 6 and 7. So the jigger on your periodic table is actually groups, I should have another pen here. Okay, are actually 4, 5, 6 and 7 and hydrogen over there. Because hydrogen will act as a non-metal as well on occasion. And they share electrons in a covalent bond. So it's a sharing of electrons. Now, whereas this an ionic bond involves donors and acceptors effectively sticking together because of charge. Now, in terms of sharing electrons, how many electrons do group 4 share? They have 4, so they share 4. So group 4 will share 4. I'm going to put more, it's hard to get that note in. Group 4 will, I'm going to say, share 4. Group 5 has 5 valence electrons. It wants to gain 3, so how many will it share? 3. Group 5 will share 3. Group 6 will share 2. Oxygen's a really good example of that. Group 6 has 6, it wants to gain 2, so it will share 2. Group 7 wants to gain 1, so it will share 1. And also hydrogen will share 1. So group 7 includes group 7, there's group 7 and hydrogen acts the same way. Hydrogen wants to gain 1, so it will share 1. And that's the nature of covalent bonds. Any questions there? Now I'll return that. Okay. So you need to be familiar with the periodic table in terms of the noble gases, in terms of what's happening here with groups. And that should all be on your periodic table right now, reflected in notes. This idea of the metals and the non-metals ionically bonding. The non-metals are also involved in covalent bonds. On the slideshow, this is the slideshow, the first slideshow, I would say 5, 6, 7, 5, 6, 7, 10. Okay, we'll write that down. Slideshow 1 is, so it's that slideshow, I would say 5, 6, 7, 10, 11, okay, 11, 13, 15. These are like, it's actually 11, 13. This is a dense slideshow because it covers all of year 9 and introduces year 10, 16, yeah, 16, yes. Okay, done. 16 through 18. So 15 through 18. These last slides, you need to be familiar with Lewis dot diagrams. You need to be able to do those. What do Lewis dot diagrams, what do we draw in terms of the dots?
Lewis doesn't have any lines, does it?
Doesn't have any lines.
It's just dots.
It's just dots, but what do the dots represent?
Electrons. And the valence shell.
If you said valence electrons or the electrons in the valence shell, great. If you said electrons, no. Okay.
Left over.
Lewis dot diagram doesn't have lines. Like Lewis no lines.
But, so
Lewis is not a line.
Make sure you don't have a phone.
So how do you show?
Okay, so Lewis dot diagrams. So, what's the Lewis dot diagram for carbon look like?
1, 2, 3, 4.
Something like that. Only valence electrons. What's the Lewis dot diagram for hydrogen look like? Yeah, just a single dot. What does a covalent bond for hydrogen and carbon look like? Just like that. So methane, I've left myself no space at all, I've overcommitted. Methane in the Lewis dot diagram looks like that. Okay? Now, if you want to put the dots side by side, you can. Okay? Let's muck around a bit. What group is fluorine in? Group 7? Who said 9? Oh my goodness. So fluorine would be, is that valid? Is that valid, what I've done just there? Yes or no?
Yes.
Yeah. Fluorine's in group 7. It wants to gain 1, so it will share 1. But, just a second, for your Lewis dot, for fluorine, you need to show the lone pairs. It's not, and you might want to write that down. Lone pairs need to show them, okay? Because people have got the habit of not doing that. So fluorine, anything in group 7, and hydrogen will act the same way. They will always share 1 to gain 1. Okay? That's a Lewis dot diagram. How is that different to a structural diagram?
There's lines showing.
Yeah, the structural diagram. So you need to be aware of that. The structural diagram shows, in this case, we'll do the same thing. The structural diagram shows the lines represent an electron from each atom being shared, and then I'll put fluorine down there again. And in the case of fluorine, you'd still have lone pairs. They need to be included. So, just a quick run around. Carbon is in group 4. It has 4, so in order to gain 4, it has to share 4. What are group 5? Nitrogen. Nitrogen has 5, so nitrogen will gain, in order to gain 3, it needs to share 3. So nitrogen tends to form structures like this with a lone pair. Group 6, an example of that would be oxygen, and it will do something like that. It will share 2 in order to gain 2. And fluorine is in group 7. Oh, fluorine. Is it FL or F? F. I'm going crazy. That's the example there. It's in group 7, and so it tends to form a single bond and have 3 lone pairs. And you need to be able to do that. Any questions about that? Okay. The next one, 3D shapes of molecules. Now the 3D shapes, we did work with that. What drives molecules to form 3D shapes? Yep.
They were like the negative energy or something in the valence shell is pushing each of the atoms away from each other.
The negative energy.
I don't know.
What's negative in their shells?
Electrons. Oh yeah.
There you go.
Got it.
Valence shell electron. Oh, that's naughty. Repulsion. Valence shell electron repulsion. Okay, is what is driving 3D shapes.
Wait, what's
The electrons in, hang on, the electrons in the valence shell are actually pushing each other away. Sorry, it is VSEPR. I've made a mistake there. Valence shell electron pair repulsion.
air repulsion?
That's it. That works. So electron pairs can be near each other because they have opposite spin, but electrons overall will repel each other. I gave you a really nice diagram for that. Do you remember? Okay, just with your arms, not hitting the person beside you, or with your fingers, that'll work too. Show me linear. It's pretty easy. Linear will work like that. What about bent? Bent or angular, it's called. Yes. Now then you have trigonal planar, triangle in a plane.
It's actually that.
Yes, Harry, that will work for me. Something like that. It's flat. Yes. Whereas when you have trigonal pyramidal, something like 3 with a couple of electrons up here. Yes. And then tetrahedral. You need to know all those shapes. You need to know all of those shapes. Now, I did give you a little rule for that. It's on the diagram on slide 1, or if you like, slide 5. So for 3D shapes, you need to know, let's see, 3 to 7 would see you right. That's it. For 3D shapes, 3 to 7. Slides 3 to 7 will see you right. Electron pair repulsion.
What's the VS?
What about it?
Valence shell electron.
Valence shell electron pair repulsion.
What about it?
We just went through that.
It just makes
Oh wait, is
3D
it?
shapes.
No, the electrons are the reason why you get a 3D shape. Not the protons, not the neutrons. It's the electrons trying to stay as far away from each other as possible. Okay. So, the rules of the game that we had before were now, how do you go about working out a shape? Start with the central atom. Now, how do we find the central atom? The one with the most bonds, which is most often carbon. Okay, find the central atom with the most bonds, then do a structural diagram of that. Don't forget your lone pairs, and then what is the rule? You're wasting time, and I'm wasting time talking to you about it. Then what is that rule?
Number of bonds around.
The number of things around that central atom, and a thing can be a lone pair, or it can be another atom. Determine the shape that is made. So if you only have, well, on that key slide on slide 5, so slide 5 is the key slide, that shape. You're not going to get given that. You will not be given that. So you need to remember this. If you have one or two things, it will go linear. Okay? So trying to think of a good examples for you. Well, just fluorine and hydrogen would form a linear shape. Okay. Now, if you have a total of 3 things, that's a total of 3, which could be 3 atoms. Nitrogen with, actually that's a terrible example, don't do that, because that's got 4. It's got lone pairs. Don't do nitrogen. What am I going to think of? No, not oxygen. Oxygen's a terrible example as well. What's my example molecule? What's a good one?
Nitrogen.
No, not nitrogen, because it's got lone pairs out the boron.
Boron.
Boron, what group is boron in?
3.
3.
Or do aluminium, it's 1 bit.
I don't even like that. Okay, I'll give you
Helium.
something like this. Okay, we'll go that one there for a total of 3 atoms and 0 lone pairs, or 2 atoms and 1 lone pair. And an example of that is water. Okay, something like that. Actually, no, that's a bad one. There is an example like that, but it's not water.
That's 2 lone pairs.
Water does. Water is an example of a 3-1. Water also forms a bent shape. If you get, 2-2. Water will do that and will form a bent shape. If you have a 2-2, you will get a bent shape. If you have a 3-1, you will go a trigonal pyramidal. If you have a 4-0, you'll go tetrahedral. If you have 3-0, you'll go trigonal planar. And if you have a 2-1, which you will never see, you will go bent. And these will all be linear. Those are the rules of the game. It's on slide 5 of that slideshow. Yes?
How can we get a 2-1?
You just won't see it. It's going to have basically it would be very, very odd. You won't see it. So, but that slide 5 covers that. Yes.
So H2O is a 2-2, is it?
That's right. H2O is a 2-2 because oxygen, which has 6 valence electrons, it wants to share 2 to gain 2, and then it has 2 lone pairs. So you get a bent shape. So if it adds up to 4, if the total is 4, you get this, this, or this. If the total is 3, you get trigonal planar or bent, and if the total is 1 or 2, it's linear. But you, yes?
For the F and H, aren't there 4 things around the center?
No, because I see what you're saying. That's probably not the best example either. But in terms of what these two are doing as a shape, they're just going to straighten out. Yes.
Why don't you just do hydrogen, hydrogen?
Okay, fine. There you go. It's more okay. Yes.
Lone pairs
Yes.
are like pairs, like 2
Yes.
of something.
Yes. 2 electrons.
2 electrons.
Yes.
Pair, 2.
And 1 pair is 1 thing that's made out of only counts to
1 pair counts as 1. Yes. Okay. The pair. Yes. It's lone pairs or actual atoms.
What do you do if you only have 1 atom, 1 electron?
You won't. There will never be given an example like that. Okay, so you'll be okay. Yes.
What is an example of a trigonal planar?
Trigonal.
What does it look like?
Trigonal planar. It's a central atom with 3 atoms coming outside of
That's
it.
what I thought.
Yeah.
But why wouldn't it just be a trigonal pyramidal?
Because the distance between
Oh, they have
that
to make it
angle
up.
there is the maximum distance.
Yeah.
If you try to change that shape, the electrons in these atoms will get closer in one way or another. They're trying to stay as far away from each other as possible. So if you go up, as soon as you go up, it actually they become closer, so that it will flatten out. Yeah. Now that let's see. Reactivity of metals. Key points there. Now I just want to check this quickly. I need to see how wide I've set this screen. Otherwise I'm going to have to delete stuff. Yep. Seems okay. Yeah. Turn it on. Reactivity of metals. The reactivity Okay, there's two key things. Now, one of the key points of understanding is some metals have been known for thousands of years. Other metals are only recent discoveries. Why is that? Yep.
Because unstable elements are not usually found on their own because they're so
Unstable. Or the magic word we're going to use that is starts with R. Reactive. Yeah.
Reactive, they're always bonded to something else.
If a reactive metal will react, and so, for example, iron will rust, yes, in the atmosphere, whereas gold is very unreactive and doesn't work that way. So you'll be given a reactivity series, and you'll be able to work with that. I'll see if I can get a copy of that. There's no reason why I can't find a copy of that, but there are plenty of activity series around. So maybe you remember potassium and lithium are highly reactive, and gold and silver are very unreactive. So first thing is, reactive metals aren't found lying around in nature as a pure element. They're always trapped in ores. That's the first thing. The second thing you need to be able to do, yes, what was the reaction that we talked about where you have one metal is with maybe something attached to it like oxide. One metal is pushed and replaced by the other metal.
Displacement?
Yeah, displacement reactions. Do you remember these? Displacement reactions occur. I should have an example here. Oh yeah, iron and copper sulfate. There's iron. Iron plus copper sulfate. Will a displacement reaction occur for that?
Yes.
Because?
Iron is more attractive.
More reactive. Yeah. So the example I gave was geeks and girlfriends and things like that, where the sulfate can be stolen away, if you like, by the more reactive iron. So you end up with FeSO4. What happens to that copper? What does it do?
Separates and chills out on the outside.
Yeah, it's copper, but where does it go in the solution? Yeah, that copper becomes a solid that will actually stick. If that's an iron nail in a solution, the copper will stick around like that. So another thing we talked about with displacement is that it pulls, what was it, the actual definition? One metal is deposited on another metal. Is actually in the definition you have in your books. Okay? One metal is deposited on another metal. The other thing you need to do is be able to navigate an activity series and judge, looking at that little activity series, is this reaction likely to occur or not likely to occur? You know? And yet, iron is more reactive than copper, so iron displaces copper. Takes the place of copper with the sulfate, and you end up with copper solid forming around the iron nail. In terms of slides for that slideshow, it's a short slideshow, it's almost everything. It is 3 down to 3 to 8 for metals. It slides 3 to 8. We'll see you right. Yes?
Should we have the S there indicating it's a solid, or like do we need that?
No, we don't look at states for you, but I'm just putting it there to remind you that the solid will form in this case out of that solution. Now, the next slideshow was the quite large hydrocarbons. Now, where can I delete? Okay, hydrocarbons, the key slide for you is, where are we? Slide number 6. That's the diagram where you have the alkanes, alkenes, alkynes. What's the difference between an alkane, alkene, alkyne?
One has 2 or more Double.
Okay, how many bonds does an alkane have?
Single bond.
One.
It has a single bond. Okay, let's step back again. A hydrocarbon contains what atoms? Hydrogen and carbon. Now, an alkane has hydrogen and carbons and only single bonds. So it is saturated or unsaturated? Saturated. It's got maximum number of hydrogens. What is the formula for an alkane? CnH2n plus 2. Yes. Now, an alkene has what type of bond that distinguishes that name? At least one double bond between carbon and hydrogen? Between two carbons. Why not carbon and hydrogen?
Because hydrogen can't have two bonds.
Hydrogen can't have two bonds. It can only share one electron. That's an insane question. Well spotted. So yes, it's only between the carbons. There's a double bond. And it is saturated or unsaturated? Unsaturated. Okay, what's the formula for an alkene? CnH2n.
That's it.
What?
CnH2n. Okay, alkane has got the single CnH2n plus 2. An alkene has a double bond, carbon-carbon bond, CnH2n, and alkyne has a triple bond, CnH2n minus 2. And you need to be able to draw. Now, what's the difference between a structural formula and a structural diagram? Completely different. Yep.
The structural formula is like a written down version of the diagram, and it's in without all the lines and everything.
Yes. So the structural diagram of something like methane, ethane. Oh, you need to know the prefixes, yes? Methane, ethane, propane. This is all on that slide. So for something like propane, actually I'm going to go one more. Methane, ethane, propane, butane. You need to fill the hydrogens in. And is that propane, propene, propine? Propane. Methane. Oh, that's not complete. Let's get that right. For something like that, you need the structural formula or condensed structural formula would be CH3, CH2, two of them, CH3. Structural diagram, structural formula. Yes? Now, the next thing you need to know is constitutional isomers. Can you draw them? You don't have to name them. What is a constitutional isomer? Or, you might want to make a note, sometimes just isomer. They'll drop the constitutional and they'll just use the word isomer. Yes?
You have it like the carbon coming off where one of the hydrogen is like up the top.
The CH3
So it's not,
So there's a chain. Yeah, I understand. There's a definition for it.
It's not a straight chain. It's like
Yeah.
up.
Yeah.
Like the same chemical formula,
But
different structural formula.
yes, same
Exactly.
chemical formula, different structural formula. So Daniel, yes, you're right. You've got wiggly chainy things going on. Okay, here is, this is a 4-carbon structure with maximum hydrogens. Is this not also a 4-carbon structure with maximum hydrogens? So if you count, you will be required to draw these. There is no doubt about it. It's the same every year. I'm not giving away the keys to the kingdom. You need to know how to draw these. So, usually the way the question is written is, draw 2 isomers of hexane. Let's just draw 2 isomers of hexane. Now, you can just draw hexane. That's fine, in a line. 6 carbons with the hydrogens around it. And then 5 carbons with a carbon sticking off the side. Anywhere that is valid. Okay? So hexane has a few isomers. Yes?
What counts as a non-valid place to stick the carbon out of?
Well, you can't, this, you've got this one here, yeah? You can't put this on the end, like that. Because it's the same as that. Yeah?
Yeah.
It's not actually, that is just, I'm trying to sneak the carbon on this side, but it's really just the same. That's a non-valid constitutional isomer or isomer. That is an actual isomer. It has a very different structural diagram, and it's got the same chemical formula, but a different structural formula. Because that's CH3, CH2, CH2, CH3. That's CH3, CH. Oh, that just reminded me if my son needs to be picked up, which he doesn't. And I have multiple alarms just for that job.
Oh God.
CH3, CH with a CH3 coming off the side, and then a CH3 at the end. Okay? So there's that. Lastly, alcohols. Alcohols, what is the functional group that designates an alcohol? OH. That is how you tell whether it's an alcohol or something like an alkane, alkene, alkyne. Yes?
Does it have a name for it?
The hydroxyl, yes. The hydroxyl group on the alcohols. So, for an alcohol, this is methane, ethane, propane, butane. What is butanol? What does butanol look like? It's going to be C, 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 C. There's your carbons, fill those in. Put an oxygen, put a hydrogen. Don't forget the lone pairs, as many, many people did on the prac. And then fill in your hydrogens. Okay? So you're going to have the same number of carbons. You have to, I'm being a bit fast and lazy here. I'm not drawing my hydrogens, but you have to. You must draw the hydrogens. So butanol would have the hydroxyl group on the end, and you would go from there. Yes?
What's the definition of hydroxyl?
Just OH, which is the functional group of alcohols. Yes. So, any questions? Yeah.
Another stem is that the isomer where you would do but 1A and but 2A?
Oh yes, but1, yeah, that is where the alcohol is. This is at position 1, yeah? So you should know, for example, that if you were given the name butan-2-ol, on the second carbon is the OH group. So this is butanol with the alcohol on the first carbon. If I did this with the lone pairs, that would be butan-2-ol, where on the second carbon I have the hydroxyl group of the alcohol. Yes?
Doesn't matter which side you go from.
No. No, they read from either way. Yeah?
So it's an isomer if it's 2-methylpropane?
You won't be going that far. But 2-methylpropane is on the second carbon of a propane methane, ethane, propane. On the second carbon of a propane chain, so it's 3 carbons, you have a methyl group, CH3 coming off it. So that's how that's read. Yeah. So we did quite a bit on hydrocarbons, and the last thing we did was fractional distillation. Do you remember that?
Yes.
That's where you have, it's called a fractionating column. I never actually said that, but it's called a fractionating column that uses, what does it use to separate hydrocarbons? How are hydrocarbons separated? But based on what principle?
Different boiling points.
Different boiling points. So heat is right, yeah, heat is right, but you need those different boiling points. Which hydrocarbons get to the very tippy top?
Short chain.
Short chain hydrocarbons, which have very low boiling points. Which ones get stuck down the bottom?
Heavier chains.
Don't say heavier. That would be very wrong.
Longer.
Long chain hydrocarbons with very high boiling points are stuck down the bottom. And while we're on alcohols and alkanes, alkenes, alkynes, which ones produce the most energy? Is it short chain or long chain? Long chain. Why?
There's more connections to be.
More bonds. Because where do you get the energy when you're burning stuff? From breaking bonds. Some of you in your practical report write-up said that more carbons were being burned or hydrogens were being burned, but of course none of that happens. The carbons you start with, you end with the same. The hydrogens all get through. It's the bonds that are being broken. So that's a really key point. So you need to know fractional distillation a little bit. That is kind of covered on that slide as well. And finally, combustion reactions. The last little bit that we did just the other day. So the hydrocarbons, I will write down the slides for you. When I send out the email, I'm going to change the red box. I'll write down the particular slides that are important. But it's almost all of it because I went through that and got rid of everything you didn't need. So it's just pretty much all critical. And lastly, with combustion reactions. If I have, what does complete combustion mean? What are the waste products or the byproducts in complete combustion? Now there's always products, atoms always get carbon dioxide and water. Great.
No waste products.
So they are the products, carbon dioxide and water. So so complete combustion has plenty of oxygen, allows that to happen. Now, incomplete combustion produces what products? Well, let's start off. Is water produced as well?
Yeah.
Yeah. Water is always produced in combustion. No matter how you do it, water is always produced. So great. But what other products are produced? Carbon monoxide in both cases. And in one case, what else?
Carbon dioxide.
Carbon.
Oh, yeah.
That's it. So for incomplete combustion, you can have water, carbon monoxide and carbon as ash or soot. And in another case, you get carbon monoxide, water, and that's it. So that's incomplete combustion. You don't need to balance the equations. You should know balancing already from year 9, okay? But you do need to recognise products, reactants and products in a complete combustion and an incomplete combustion reaction, and you need to know what those things are. Any questions? That is it in a nutshell. So I'll stop that.